This is an elimination reaction. What makes an elimination reaction? Why do we call it that? Let's do the reaction. Look at it more closely and see what's going on here. So notice what has changed. Leaving group, we know about those. Leaving group is gone. It left. What else is missing? This H is gone. We could say it was eliminated. So the leaving group leaves, just like in a substitution, but unlike in a substitution, it was not replaced with a new group. So over the arrow, in order for an H to be gone, we need something that likes to take H's. Hence, you will see the base play a key role. So let's put a lone pair there. Let's even make it negatively charged. So what it's going to do is it's going to take that H. So that'll explain why this carbon's missing its H. Notice there's something special about the carbon. It's the carbon attached to a carbon with a leaving group. So if we say the carbon with the leaving group is our alpha carbon, we could say the carbon attached to it is a beta carbon. So this would be therefore a beta H because it's on a beta carbon. So the alpha carbon is the carbon with the leaving group. If there is a beta H, a base can come along and take it. Remember, the electrons stay behind. Instead of letting them land on the carbon, I'm going to do this maneuver. Go bond to bond. That forms this pi bond here. That explains what happened here, right? So if we color that in, these electrons went here. And then the leaving group left. So let's indicate that with the arrow. Why did the leaving group leave? In order to form this pi bond, this carbon had to let something go because it would have a full octet when it's done, so it would exceed its octet if it kept the leaving group bond, right? So 3 arrows here. Base takes the H, the electrons from the H go to the alpha beta carbons to make a pi bond, right? So those are still our alpha beta carbons. And the leaving group left. Okay, so we call this an elimination reaction. So there's different varieties of elimination reactions. It's going to be a master sort of category. So it's any reaction where not just specifically the one we drew up here. We try to make this as general as possible by having the leaving group as a variable. But it's any reaction in which a molecule loses atoms or group of atoms to form a new pi bond. So we eliminate, the word eliminate means to completely remove something. So we don't replace it like we did in substitution. Okay, so I named these for you, the carbon atoms with the leaving group. We use the Greek alphabet to name each carbon. So that's our alpha carbon and that's our beta carbon. So we took care of that. And we'll be using that terminology frequently to label them and refer to them. The carbon that lost the hydrogen atom, that's always going to be your beta carbon. So the one I just drew up there is elimination of the variety. Just like at substitution, there's different flavors and varieties. It's going to be E2 because I drew that all second order style, all those arrows in one step. Okay, so the full name I'll write again one more time down here. I have a space for that. Okay, so what can we think about functional groups that would be useful for this? So look at what we make. So we start with an alkyl halide, right? So our starting material is an alkyl halide. Our product is an alkene. So in other words, we make pi bonds. So there are just about any alkene. When we want to make an alkene, we see an alkene as the product. We're going to be thinking elimination now. Okay. Possibly even alkynes. Right? We're going to work our way up to that, where we have 2 pi bonds. Plus, there are others that can be formed by elimination. Other pi bond containing groups. I'm pointing that out so you know it's possible. but we are going to focus only on alkenes and alkynes for the most part. So let's do an example with real R groups drawn in there. So here's an alkyl halide, okay? Now, when we see an alkyl halide, the only thing we've done in the past is substitution, replace this. Now we're gonna be thinking about, you're being told to turn your mind to elimination. So if we're doing elimination, we gotta say, okay, I gotta find my alpha carbon. In order to do that, I gotta find my leaving group. Where's my leaving group? Chlorine. All right, that's my leaving group. Attached to my leaving group must be my alpha carbon. Attached to my alpha carbon are my beta carbons, if there's more than one. So, and I do in fact have more than one. Notice that it didn't matter which one I picked because of the symmetry of this molecule. I could have addressed either one, so we'll talk about when it matters later, but to work, we got to work our way up to that, right? So this one has the H drawn in for you, so that is, of course, the one we will look at. But I could have just as easily picked this beta carbon, and it's beta H. Okay, so there's my beta H. Now we're ready. We're going to treat whatever's over the arrow. If we're told we're doing an elimination reaction, we're going to treat whatever's the arrow as a base. Who's our base over the arrow? Well, we have sodium methoxide, and we have methanol. I don't know about you, but that we know is a weak base. That's a stronger base. They're kind of related, right? This is the conjugate base of this is an acid. So this would be our solvent. This is our base. Go ahead and draw your lone pairs. And let's do the 3-arrow mechanism. Base takes the H. I think I'm on my pen now. Yes. Base takes the H. Beta H. The beta H's electrons stay behind and go to make a pi bond between the alpha beta carbons. That ejects the leaving group. Those 3 arrows need to be drawn in order to be done with your E2 reaction. In between the alpha beta carbons, I have my pi bond formed. This is a concerted mechanism. Notice those 3 arrows were not drawn in several separate steps. They were all drawn in one step. So this is a concerted mechanism. Knowing it's concerted and we didn't make separate species at each step along the way, that means they have to interact at the same time. So our rate expression is going to depend on the presence of both species. The substrate, which is the thing with the leaving group, right? And the thing that reacts with the substrate, in this case, a base. Notice the 2 components there, hence it is second order. Now you know where we call this the E2 reaction. Bimolecular elimination. Okay, so let's look at some features of E2. We're going to take for granted and build on what we understand about energetics, transition states, and etc., but we will look at those components for E2 as well. Okay, so I'm going to do another example reaction, and I'm going to kick up the difficulty a notch by introducing some stereocenters, some 3D spatial arrangements to think about. So what I'm going to do is I'm actually going to draw in, since my leaving group is part of the mechanism and it's attached to a stereocenter in one case and adjacent to one in the other, I'm going to make sure that I'm drawing everything in so I don't overlook something important there. Now I'm going to find my leaving group. Not too hard because it's actually labeled Lg. So Lg. Now that means it's attached to the carbon called alpha. That carbon is attached to other carbons. Only one carbon is shown, so that for the purposes of this exercise, we're going to only look at that one. So we don't know what the R groups are. We're going to assume that that's not the intention of us to react those because I'm doing sort of a template here. Now, here's the thing we got to be concerned about. Let's go ahead and start now we found beta carbon, and here's our beta H. Let's draw our lone pair on our base so we could do our mechanism. It finds that beta H. It's going to leave its, it doesn't matter whether it's a dash, a line, or wedge, it's going to leave its electrons behind, right? And leaving group leaves. So you can still draw a mechanism on a dash or a wedge, right? You could draw all those arrows. Now, I don't know about you, but I see two different ways to draw the product. So before I fill in that box, here's my alpha and beta carbon with an alkene. I'm going to draw it two ways. So on the beta carbon, oops, I had drew it the opposite of way it is there, so that we keep confusing. Let's do beta alpha and beta alpha. Now let's fill in what's on the possible product alkene after elimination. So on beta, H is gone. So I have R2. I also have R1. And on the other side, the alpha carbon lost its leaving group. So I only have an H left and an R3. But notice, what if I had done this instead? R1. Instead of putting the H on the top, I put it down here and the R3 here. These are not the same. These are isomers of each other. So notice that there are stereoisomers of each other. Specifically, notice that same connectivity, but the H is in one case syn, or on the same side as cis2, the R2 group, whereas in the other one, it's actually the R3 and R2 that are cis to each other. The H is cis to the R1. So knowing that these are different, which one am I going to make? There's only one possible, and that brings in our new rule. It's kind of similar to, it's a key feature of the mechanism. Just like SN2 required backside attack, E2 requires opposite attack of the H from the leaving group. But this is the anti-orientation we're going to refer to this as, because it's not really the same as attacking a carbon. It's taking the H away. So it requires anti-deprotonation of the H on the beta carbon. So how do we see anti-relationships best? In other words, we want to make sure that the beta H must be anti to the leaving group. So we're going to have a big question mark here, and it's going to be beta H must be anti to Lg. Okay, that has to do with orbital alignment, right? So if the beta H, if you're going to make bonds from taking the H off and using its same electrons to use a pi bond, we have to have the orbitals aligned so that when the leaving group leaves, it's actually ready to use that orbital to fill the pi bond. So how does that work? Beta H must be anti. How do we see anti relationships? Anti-periplanar is another way to phrase it. And that might ring a bell to Newmans. Newmans are one of the easiest ways to see that. So let's look. We have to look down the alpha-beta bond or beta-alpha, your choice. But either way, we have to include those in our Newman. I'll do alpha-beta. Okay, let's take a look. So alpha's in the front here, leaving groups up above my head. Try to get ahead of me. Who's on my right? H, right? R3. Now we're staggered, so that means we have R1 down at my feet. Who's up at your right? That dash is still on the right, correct? The two H's. And not any H, this is our beta H. And then R2 is on the other side. Okay, so here's the issue, is Lg and beta H are not anti right now. They're not in the orientation that will allow an E2 to happen. They need to be anti. So we're going to rotate. I'll rotate, let's rotate the back. So in other words, that means I'm going to leave the front the same. Lg, H, R3. I'm going to rotate the back until I get that beta H down here. Now let's think about how we had to do that. That means this came down 1, R2 came over to this side, so I need to put R2 there, which leaves R1 for that side. So R2 goes there. There's my leaving group and my beta H. Now they are anti. I get to do this rewarding circle. It shows their anti-relationship. This is what will be gone. They're eliminated. The beta H and the leaving group are gone. In between these two carbons, the alpha and beta carbon, we are going to be forming a pi bond. This right here shows us the final relationship between these groups. So let's circle it just to kind of emphasize that. R1 and R3, they're on different carbons, but on the same side. R2 and H are on different carbons, but on the same side. Now we know what to draw. I'll write that here. Same side. We use the phrase they're syn to each other or cis to a pi bond. So we'd say the R2 is cis to the H, or the R2 is syn to the H. They're on the same side as the pi bond. Let's draw our final pi bond, our final answer. Okay, so drawing your 4 groups coming off the pi bond. Who's on alpha? Well, LG's gone. Alpha has a R3 and a H, so just draw that anywhere you want. Don't worry about where you have to worry about this is the part where your brain needs to kick in. Who's on beta? Beta is the back carbon. It has a R2 and an R1. All right. Where does R1 go? Let's just pick one of them to be responsible for. R1 must be on the same side as R3. So of these two positions, R1 is going to go on the same side as R3. That means also on beta was R2. Let's double check we did that right. R2 must be on the same side as H. R2 is indeed in that green circle, that same side as H. So these are syn to each other. These are syn to each other. These two groups are on the alpha carbon. R3 and H are on the alpha carbon. R3, oh, I wrote R3 twice. So I'm glad I talked through this. R3 is on the alpha carbon. R3 is not on the beta carbon. On the beta carbon, we have R2, and this should have been R1. So I apologize if that was confusing. There we go, R1. Okay, so R3 and R1 are on the same side. H and R2 are on the same side of the pi bond. Alpha carbon has R3 and H. Alpha carbon has R3 and H. Beta carbon has R2 and R1. Beta carbon has R2 and R1. We're good. Who did we match? Of the two possibilities, do we see a match? So what if this was a multiple choice problem? You drew out this answer, you now have to find the match, right? So you look for H, you look for these syn relationships. H must be on the same side as R2. So there's H. It's on the same side as R2 there. It's not here. So this was the correct one. If this was A and B, you'd pick A. B would be wrong. Okay? That comes from the mechanism that the beta H must be anti to the leaving group. So yes, Newmans are back with a vengeance. When do we need to draw Newmans? Only when we have the scenario of there's only one beta H possible to pick off. So we have to make sure we rotate so it's in the right alignment. Okay, I'll show you examples where we might not have to make that consideration soon, but now you know. It doesn't hurt to do it. It's just, it could be excessive. Okay, so we've alluded to the fact that this is all a concerted mechanism. So that means the transition state will be only one species, right? And so what's going on in the transition state should embody what we see in the mechanism. So I'm going to kind of draw this straightened out just to simplify this a bit. So R1 and R2, here's our, I'm draw all the sigma bonding framework, R3 and H. Okay, now let's draw our leaving group. I'm actually going to erase this one because I should have drawn a dotted line. Remember, the H is breaking its bond. So I'm going to draw the leaving group. All right, so here's our substrate, and we made sure that our alpha carbon is drawn. Alpha carbon has the H, yep, as the leaving group, excuse me. Beta carbon's there. Who's going to take the beta? So this must be H beta. Our base comes along in the same line of sight as the H, and it starts to make a bond to H, dotted line. That means it starts to break its bond to that carbon, which is why that gets a dotted line. The carbon is losing the leaving group, right? The arrow is drawn to show that coming out, so that means we draw a hybrid of that, which means a dotted line here. The base has an arrow coming here, which means we draw a hybrid of that, which means a dotted line there. And then this is about to leave. This is a breaking bond, so we draw a dotted line there. We're also forming a pi bond. So we should keep the sigma bond, that never gets dotted, but we have one more line to draw, is the new pi bond is dotted. All things that are not the same in the starting material and the product are dotted. So bonds that got broken or formed are dotted in the transition state, okay? This bond got formed, this bond got broken, this bond got formed, this bond got broken. All right. Reaction coordinate, that means we're ready to fill that in. This will be TS, and I'm going to abbreviate that on the plot so you don't have to draw it over and over again. Okay. So a generic reaction coordinate will look like this. Just like before, energy. This is our reaction coordinate, our reaction profile. Reactants. So we have our R with a Lg and a base. We have our transition state. And then we have our products, which is an alkene, right? We're mostly concerned with the organic product, but yes, the leaving group's off somewhere as an anion, the base became its conjugate acid. So there's all those other things there. But what we're really tracking is the organic substrate changes. So let's connect our dots. Ooh, that should look familiar. Just that single simple plot. Looks identical to what? SN2, right? That's because they're both second order. Concerted mechanisms. Only one transition state. That's what they'll look like. We're assuming it's spontaneous, right? So we're going to have this, it's our delta G of reaction, where we have our products in lower energy than the reactants. And then various factors will dictate how easy it is to overcome this activation barrier, known as our activation energy. Okay. Similar but different. Don't worry, we'll do a cross comparison at the very, very end, but we want to, it'll be more helpful to look at this separately first. Okay, so we've talked about the different, when we have to really think about what our product's going to look like. We just don't willy-nilly make an alkene and call it a day. We got to think about where it's going to go. So like we saw here, there were two possible geometries for the alkene. And so that's a special consideration that might require Newman. So when do we see that? When the beta H has only one of them, and so we have to rotate it into position if it's not already in position. Other considerations as we look at larger molecules. So let's expand what R is. What else can be around us? So look at this scenario, for example. What makes this have a little more complexity? Well, let's do what we'll always do when we know we're going to do an elimination. Find your leaving group. We can all do that. Bromine. Find the carbon attached to the leaving group. Who's that? That's alpha. Label all carbons attached to alpha as beta. Well, look at this. We've got beta, beta. And can we agree those are equivalent betas? because they're just carbons with an ethyl, they're the same group. So this alpha has two ethyls attached. So that means the base has no particular preference for one beta over the other, right? So I'm going to go ahead and use the same color for that one. But there's one more beta, and that's this methyl here. And that is different, right? Because that's not an ethyl. So I'm going to label this one with red. How about I do green for the betas that are different, the ethyl betas, just so we don't have the blue mixed in with the alpha. Okay, so when all our groups are not equal, we have to also have another way to have different outcomes. So notice that we could take, let's draw in our possible H's now. So beta H, yes, this carbon has 3 H's. All of those H's are equivalent, right? So there's no reason it would take one over another. So in the future, we will probably only draw in one, but I'm just gonna spell that out right now. So the idea is if the base takes off this H, we're gonna have a different product than if the base takes off this H. And so the two possible products are shown here. Let's see if we can match them up. So we could get a pi bond here. Well, just for simplicity, that means we didn't take that one. We took the other one that's equivalent. Let's draw on that one as well, just so we don't confuse ourselves later, beta. Okay, so the green betas are equivalent. We have a choice of 4 of them, and they would give us the same result. Let's draw the green path with green arrows. Let's put our lone pair on. And here it comes. Let's take off that one. Leave electrons there between those alphas and betas. So that's how you know where the arrow needs to go. As soon as you get your beta, once you decide I'm going to try taking off this beta H to see what happens, those electrons have to get shared between the beta carbon and wherever the alpha is, which is here. That allows this leaving group to be ejected. Kick out the leaving group. So notice that matches this product. The pi bond's here, right? That's our alpha beta carbon right there. So let's box that in with green. That's our green path. Let's look at the other one. Look at the names here. Zaitsev. This is going to be our so-called Zaitsev product. So they're going to have names. We'll talk about that in a minute. Okay, look at the other one. How do we form this? That means one of the H's here is missing. See, there's only 2 H's. If we draw that in, there's an H here, an H there, right? Whereas there's 1 H there. So we could see the H that was missing. We missed, there's only 1 H left here. Here, there's 3 H's, we're down to 2. We took one of those red betas off. So let's do that path with red arrows. Take off one of those, and the leaving group leaves. Let's box that in with red. This is called the Hofmann product. Okay, there's a difference there, and we can actually, what chemists love is when they find out there's more than one option. They love to engineer ways to favor one over the other, to increase selectivity, to control, form of control, right? So this base wasn't defined. It turns out that you can tweak reaction conditions. So you could actually tweak the inherent structure of the substrate, make it bulkier, for example, or less bulky, or increase the bulkiness or decrease the bulkiness of the base to favor one over the other. Which one do you think would be favored in the presence of a large base? Well, the numbers are here for you. Look at that. Overwhelmingly, a large base prefers this one. Can we see why that is? Notice that this is less substituted. This methyl versus ethyl, it's on the periphery of the molecule, right? So if you're a large, huge base, you don't want to get way in there and through this crowded space. You're more likely to successfully pull off a proton that's on the periphery. These peripheral ones are not an option because they're not beta H's. So the only beta H on the periphery is this one. It's one of these 3, right? So no surprise that the larger the base, the more preferred. And just like everything in life and in this class, it's not a black and white deal. And it's not two extremes. It's a lot of gray area, a spectrum. Okay, it's not even black, white, and gray. It's a gradient. So we can adjust the distribution. To simplify it, we'll talk about major and minor. So we would say, okay, this is only 9% form, so Zaitsev is minor when the base is bulky. Hofmann's major when the base is bulky. We can flip that ratio, and in fact, this is the majority of the time because we often don't use a bulky base unless we have a plan, like a devious plan to have steric control. So ethoxide is a really popular, easy, cheap base. And if we were to use that, nice, but it's small. So if we use a small base, we're going to heavily favor the Zaitsev product, but Hofmann will still form, still possible. So we get a distribution. So we're going to talk about major versus minor, okay? So Zaitsev is actually favored with most bases. But I put in a few examples of bulkier bases for you after ethoxide, things that are more bulky. So I'm going to put only favored with bulky bases. So what is considered a bulky base? The bare minimum, and it's often sometimes still not bulky enough, I'll tell you, because this is where we have our transition point, is T-butoxide. We still get like almost a third, right, or a quarter to a third of Zaitsev product. But if our substrate was less bulky, we could actually still get major product Zaitsev. So this is kind of our wild card. It's actually more often, it's not safe to assume it's bulky enough. So when we really want to be bulky enough, it's really loud and clear, like this guy. Looks kind of like a spider, almost, partial spider. This huge three-legged beast here. Notice that massively swayed it toward the Hofmann. Okay, so we labeled our products, Zaitsev and Hofmann. Major and minor depends on how we controlled it with bases. Okay, so I'm going to summarize that data table here. Much bulkier bases will favor the Hofmann product. So some we'll need to be aware of, okay? So you'll say, how do I know if it's bulky enough? Well, you'll have to just know a few. Yes, that means memorize like 3 or 4. But that's the concept behind it, is why it works that way. Why? Because the bulkier bases can only access peripheral H's. I'm going to expand on that because interior H's are harder to access, more blocked, right? We would call this more steric hindrance. So interior H's are sterically hindered by their neighboring groups. Hindrance. So some we should be comfortable recognizing. So I'm going to throw in T-butoxide. So it's often written TBUO minus, TBUOK. That's our bare minimum bulk. But the problem is it will do Zaitsev and Hofmann. Okay, but it only really favors Hofmann. If you want to favor it, you got to amplify it by also making the substrate bulky. So I'm going to say amplify with bulky substrate. So if your substrate's not bulky, it's most likely to still give you Zaitsev. It's just not quite enough, but it's at that borderline. So if your substrate is bulky, so it's still hard to get into those other H's, then T-butoxide's good enough. Ethoxide still wouldn't cut it. Another really good one we've looked at before is LDA, or diisopropylamine. So it could be in its conjugate base form, which is an even stronger base. Diisopropylamine. Very bulky. So notice that has the two arms that are isopropyl create more bulk than the one T-butoxide, T-butyl group. So ethoxides are great, but not for bulkiness. Another amine that's really nice is triethylamine. Triethylamine. It's also abbreviated NET3. Okay, so if you really want to stick with one that's not nitrogen based, because there's a lot of nitrogen ones, or an alkoxide with R is bigger than T-butyl, like the one above, right? So if you see something that's like obnoxiously huge, you gotta let that be a red flag to say, it's trying to have some steric control there. T-butoxide is not always a red flag. It's the one that's annoying, that's just not enough to give you it's too close of a call. You gotta evaluate other factors. Okay? So, why don't you practice drawing this again and kind of cover the answers and see if you can come up with the right products before we move on, because it's going to get in more detail. I think it's a good time to pause. See you back soon.